Okay, Zhengfeng.
Yeah. Thanks, David, for the invitation. It's my great honor to give a talk here. First of all, I should say that my background is in quantum information theory. So I'm neither a mathematician nor a physicist. And talking to this audience make me a bit nervous. And I should apologize beforehand if you have any questions that I cannot even understand. So this is a talk about recent work. Initially a complexity theory results, but has connections to Connes Embedding Problem. And I made some effort to adapt the slides so that it may be more tailored for this audience. But let's see how it works. So complexity theory side, this is a result of our characterization of multi-prover interactive proofs with entanglement. The title of the paper is Mpa star equals RE, appeared earlier this year. And this is a joint work with Anand Natarajan, Thomas Wittig, John Wright, and Henry Yuan. So because this is a complexity theory approach, I will first introduce a bit about complexity theory that we use in our proof. So first of all, we need the notion of Turing machines. I guess for people in the UK, that's a standard common knowledge. And a Turing machine is a mathematical model of computation that defines an abstract machine. And there's a tape and there's a head on the the blocks on the tape and head moving along. And the transition rule is a finite table of rules, and that defines a Turing machine. And even though that's a very simple model of computation, it's not so different from these powerful desktops that we have, or even supercomputers we have today. The halting problem is a problem where we ask, given a Turing machine, whether the machine terminates or halts within finite number of steps. And it's well known that there is no algorithm or no Turing machine to solve this problem. And this is a very simple application of the diagonalization technique, like how you prove real numbers is not countably infinite. And the class RE is then the set of problems that is as hard as, at most as hard as the halting problem. Recursive enumerable. Basically, you can list all the yes instances of the problem. So this is Turing machine. And another piece that we need is about proof verification. So it has a connection in terms of Turing machine. We are talking about non-deterministic Turing machines in that setting. And alternatively, you can think of this as proof verification. So you have a statement and you want to know whether it's true or not. And it will be like easier if you have a proof alongside, right? So this proof is, in some sense, modeling the non-deterministic choices of Turing machines. And so, like in the simple model of MP, you have a verifier and a prover trying to convince the verifier of certain statement by sending a proof, a written down proof. And the verifier needs to verify it, like whether he or she would accept the proof or not. So that's the model of MP, and it's the biggest problem in theoretical computer science, whether MP equals P or not, whether there is, like, given the proof is really a helpful thing or not, or if MP equals P, then any problem in MP would have a parameter time algorithm, meaning that you can find the proof yourself. And like generating this model to this interactive setting may seem a minor modification to the class or to the model. But nevertheless, later on, people find out like this interaction model where you can talk to, the verifier can talk to the prover, even though the capability of the verifier is still putting the time. In that interactive setting, the power is much larger. It turns out to be p-space. Very interesting that even though like IP and p-space are completely differently motivated models. And the technique that allows us to prove this statement is called arithmetization. Basically, you convert problems in logic, like satisfiability problems, into a problem of polynomials. And you can ask questions like, given a polynomial, does it have low degree and it vanishes on certain subcube of its domain? So that's what we need to use in our proof. And so this line of development end up with this celebrated theorem called Pcp Serum. And in Pcp Serum, you would consider so-called probabilistically checkable proofs. And it's a simple proof check verification model where you have a verifier, and still you have the proof, but the verifier will not read all the bits. It will instead flip all random coins, 0, 1, head and tail coins, and then determine where to look at the proofs, only Qubits from the proof. So if there is a verification scheme like this, we can see that the problem is in PCP with parameter R and Q. Then the Pcp theorem states that PCP of order log n randomness and constant number of queries characterize MP. So all problems in MP has a proof of this particular form. And if you think about the meaning of this theorem, it's really unexpected, I should say. Basically, what it says that you can write a data format to write proofs so that it's very easy to check. You randomly look in the proof. If there's an error, you should be able to see the error very frequently. And so that's very counterintuitive. And this is also something that we would use in our proof. And at a very high level, you can think of this as a way to reduce the amount of bits you need to read, or the number of information the verifier need to see in order to be convinced of certain statement. And a technical part of this is a development of the arithmetization technique. And remember that we talk about this idea of arithmetization. You have a problem of polynomials, and an important fact that we want to know is, given a polynomial, whether this function, whether it is multilinear or low degree polynomial. And there's a test called, a very simple test called low degree test. And so that's one of the key techniques that used to prove the Pcp theorem. And it turns out to be also a key ingredient in our proof of the MIP star equals to RE result. So that's basically 3 slides introduction of what we will need from complexity theory. So move on to the problem. I will briefly introduce Connes Embedding Problem and Tsirelson's problem. I guess most of the people here are more experts than I am. So Connes Embedding Problem is about this particular embedding problem in phenomenon algebra, and it's proposed by Alan Connes in a paper, I guess in '76. Like he mentioned this problem in the paper in a line, and I guess nobody picked this up in the next 10, 15 years after this paper. But I guess early 90s, there's other problems known to be equivalent to this Connes embedding problem, such as Kirchberg's QWEP conjecture in sister algebra, and also Tsirelson's problem that we'll see today most frequently. And this equivalence characterization of the problem like make people more interested in this problem, and now I think it's a very important core conjecture in core problem in the theory of operator algebra. So maybe like what I was trying to convey is why this problem has anything to do with complexity theory. If you look at this problem, it's about infinity dimensional operators, and well, even though it's talking about infinity, and complexity theory usually is about finite structures, right? Whether you have polynomial number of steps of solving some problem or not. And that connection is all that, at least in our paper, is going through Tsirelson's problem. And there's a very interesting history. Tsirelson studied this problem and I guess published in a survey paper in early 90s, claiming this problem to be true, but later on people asked him for a proof, and then he realized he's assuming something like Connes Embedding Problem implicitly in his ideas. So he formalized this as a problem. At the time, it's not known to be equivalent. The Connes Embedding Problem will imply Tsirelson's problem, but nowadays we know that these problems are equivalent. So what is Tsirelson's problem? To understand that, we need to discuss the correlation sets. So these are very simple convex sets of like given R and S are two integers. The correlation set CQ of the of size R and S is a vector, a set of points in R to the R square S square. And so the condition that we require for this points is there is a vector, unit vector in the tensor product of finite dimensional Hilbert spaces HA and HB, and also POVMs, AXA and BYB. So X is what we will call question index, and A is answer index. So A is the outcomes of the POVMs. If you sum over A, this gives you identity for all X. And similarly, if you sum over B, this gives you identity. And we require that for all XY and AB in that range, this vector P XY AB elements would equal to phi star A tensor B and phi. So because we know that these A and B's are POVMs, so for all X and Y, if you sum over A and B, this will give you identity, tensor identity, and this is a unit vector, so it's a 1, right? So for all X and Y, the vector A and B gives you a vector of probability. And then CQA is what we need is a closure of this finite dimensional vector definition. So it's closure of CQ. Interestingly, there's another set that are we need to consider. It's called CQC. There's only one. It's almost the same, but there's only one Hilbert space. It's a single Hilbert space H, a unit vector. You also have A and B, but now they are acting on the same space, and we further assume that A's and B's commute for all X, Y, A, B. And then this condition is that the P vector should be expressed as phi star AXA BYB phi. There's no tensor structure. So these are three correlation sets modeling different ways to define what it is in that you can use in quantum mechanics. I guess this one would be what we will be like in our paper and in this talk, we would be focusing on this finite dimensional definition. But in the end, we will see consequences about the relation between CQA and CQC. So this sets are like CQ is contained in CQA and CQA is contained in CQC. That's very easy by the definition. And also there's a set that I didn't define called C-log. Basically, it's a classical correlation set where all these operators are commuting. And I should mention that we know that this classical set C-log is different from CQ. And that's basically Bayes' inequality. And there is a hyperplane to cut this set so that the CQ is much bigger than C local. And we also know that CQ is not closed, and this is a very recent result by William Slofstra a couple of years ago. And then I guess it's also based a lot on this quantum information science technique that we are able to show CQ and CQA are not equal. And because like CQA is a closure of CQ, what he's able to prove is CQ is not closed. And CQA and CQC are both closed sets. Tsirelson's problem is asking whether CQA and CQC are the same for all I and S. And so that's a very concrete definition of what Tsirelson's problem is. So for this talk, I would need the notion of nonlocal games. I know that people in mathematics don't like, or they don't work with this notion very often, but to explain the intuitions that we had in the proofs, it's important, but it's a very simple object. So basically this is an extension of the proof verification idea. Like in interactive proofs, we have a prover and a verifier. Now in this model, we have two provers. They do not communicate with each other, but the verifier can talk to them and give them questions and receive answers and make decisions. And classically, that's also a very interesting model where people in the early 90s proved that MIP equals NX. So the set of problems that has MIP is the same as non-deterministic exponential time. And in our case, we would allow the provers to show entanglement. So that's a key difference. That's how when this MIP star, the star stands for the shared entanglement between Alice and Bob. They can have a global state before the protocol starts, but they cannot communicate with each other. And the relation between this nonlocal game and the correlation set that we defined in an earlier slide is that these are optimizations over the correlation sets. For example, the well-known CHSH inequality is some linear functional of these points, right? It's if you take this average value into this summation, you can see that it's just some linear combination of these points. So that's a connection. It like allows us to use a lot of techniques from multi-prover interactive proofs to study Bayes inequalities and also the correlation sets. So like a definition for nonlocal game. It's a very simple definition. So you have four finite sets. X and Y are question sets, and A and B are answer sets. The game has two messages. The first message is from the verifier to the prover, and the second message is from the prover to the verifier. So the verifier would sample a distribution over the question sets. So mu is some distribution over X and Y. And then the decider describes how the verifier makes his decision whether to accept or reject. And so given X, Y, and AB, you will accept or reject. And in our work, we would, so this is give you a definition of one game. We will be considering families of games and in a uniform way. And for this, we need to extend the definition a little bit and consider families of games defined by verifier V, which is a pair of Turing machines, S and D. Basically, the Turing machines, S is taking care of the question sampling procedure, and the machine D is taking care of the decision-making procedure. And so they have input called, the first entry of the input is N, is index, controls the size of the game. So the nth game of this family would be defined by Vn. So you hardwire this index to N. So because we mentioned that nonlocal games are just linear functionals or equivalent, you can think of it as hyperplanes over the correlation sets. So basically what we're doing here, we define a family of linear functionals from a pair of Turing machines, S and D, S being the sampler and D being the decider. And for games, we need to define two values. So the value for a game G, or at using this point P in the correlation set, is defined as expectation over the question. That's how you choose the verifier, choose a random question, and you summation over all p x y a b, where a and b are accepted by this decider given this x and y. As you can see that this is, as I have claimed, it's just some linear functional of this p vector. And so now we define the two values. One is called entangled value, one is called commuting operator value. For the entangled value, value star of a game G, you just take the maximum over the value GP for P in this CQA, the closure of the finite dimensional strategies. And in some sense, this characterizes the complexity class MIP star. Basically, this class corresponds to approximation of this value of certain size, which we didn't specify. And the commuting operator value is an optimization over this CQC, the commuting operator correlation set. Now, because Tsirelson's problem is about whether CQA equals CQC, so if Tsirelson's problem has a positive answer, meaning that CQA equals CQC, then we know that these two values are essentially the same. So that's one consequence of or the Tsirelson's problem as it initially formulated by Tsirelson. Now it's time to see some consequences of Tsirelson's problem. So we will have two algorithms. The first one is very simple. It's exhaustive search for better tensor product strategies of increasing Hilbert space dimensions and approximation precisions. And while you can like fix dimension D and some error ratio, error approximation precision, you can make like some sort of ipson net in the space of matrices, and you can prove that this will give you a way to compute this value from below. So you would come up with a sequence of values. If you like have unlimited power of computation, you can approach this value from below. The second algorithm is more interesting and non-trivial. In our community, in quantum information, it's called Mpa Hierarchy. And I guess for mathematicians, it's sometimes known as non-commutative positive Tsirelsons. Basically, it's about the condition that you can have, like you have a bunch of non-commutative polynomials, and they define a certain region, and whether some other non-commutative polynomial, you do some maximization problem, and there's some interesting theorems here by Halting and McCloud. So what this algorithm gives us, like you can turn this positive Tsirelson into an SDP, and we know how to solve SDP, but it's a hierarchy. You have to increase the degree to infinity in order to show the convergence. And what this algorithm will give us is a sequence of values to converge to this convolution operator value from above. So algorithm 1 actually establishes that MIP star is contained in RE, because what RE is to you need to find a Turing machine so that for any problem in MIP star, if it's a yes instance, then the Turing machine would eventually terminate and tell you that it's a yes instance, and that's how we define RE. So what you can do is you can use algorithm 1. Like if you have a problem in MIP star, meaning that if it's yes instance, value will be high, the quantum value, the value star will be very high, like close to 1. Otherwise, will be close to 0. So you can see this by running algorithm 1 and to see whether the value can go above like half. So that's easy statement to show that MIP star is an RE. But in computability consequence of Connes embedding conjecture and Tsirelson's problem is that if one of them is true, it implies an algorithm to approximate the value. What you can do is you alternate these two algorithms, because these two statements being true would imply that the star value and commuting operator value is the same. And then we can use these two algorithms, right? You run algorithm 1 for a while, and then you run algorithm 2 for a while and back again. So you switch between these two algorithms, and then you have like a sequence of two sequences of values converging to this single point. And this would give you an algorithm to approximate. If you can tolerate an epsilon error on this computation of the value, then there is an algorithm. So that's something that we will rely on to disprove Connes, because what we will be using is what will be proven is an algorithm. There's no algorithm to do that. So you can reverse the arrow, so there's no algorithm, then Tsirelson problem is false, and also a Connes embedding problem is false. So what we prove is characterization of MP star, and no algorithm can approximate this value. And also we, as I said before, we give an active answer to Tsirelson's problem. I think it's interesting to think of this result in a way that you can find some problem where infinite quantum systems cannot be approximated by finite ones. And so in terms of the correlation sets, it's separation between CQA and CQC. You can think of it as a very theoretical proposal for some sort of experiments that can be done for test whether you can have truly infinite dimensional systems in nature. Like you can do Bell tests for testing whether the world is classical or quantum. But we're not quite sure, like it is a mathematical proposal whether there's physical systems out there that satisfy the relations of the operators that we design. It's another question. And also via known connections, we disprove Connes embedding conjecture. And these are known 10 years ago in the community. So that's our main results and implications. Do people have questions? I'll move on to talk about proofs. If no questions, I'll give you first an overview of the proof, and then move on to talk about more about the techniques that we use. So the technical theorem that we need is a compression theorem. So that's a picture that you should have in mind. That's why I have to introduce nonlocal games. So in nonlocal games, there's questions and answers, and these are encoded by it's some finite set, but you can imagine that you cannot encode them by some string of bits. The compression is a procedure where you start with some game and end up with some game that are much smaller in terms of the size, the message size you send to the approver and you get back from the approver. Also, the verifier is smaller, meaning that the running time, like the decider has to make a decision, and that's also smaller. And so that's a more formal statement. There is an algorithm called compress, which is a transformation from one like input pair of Turing machines, verifier V, to output verifiers V compressed, V sharp. And the condition that we have is basically the compressed game of a smaller index n can simulate the input game on a much bigger index 2 to the n. So if you like the game V on index 2 to the n has value 1, then so is a compressed game. So this is a much smaller game. You can notice that. And if the value is at most a half, then the compressed game also has value at most half. So that's very strange. Like this is some problem that has some intrinsic complexity, but nevertheless, what we proved is that it doesn't really depend on the size. The size is 2 to the n, and now it's a much smaller size game that you can study. Also, we for our proof, we proved some bound on entanglement. The compressed game, even though it's a compressed game, the prover side would still need that amount of entanglement. So this V sharp of index n would need amount of entanglement that V on index 2n is using for example, a strategy of value at least a half. And also we have some lower bound that only depend on n. So that's 3 technical conditions. Basically, the first 2 are easy to understand. We can simulate, in some sense, a big game with a small game. And also we can prove that the small game uses at least this amount of entanglement of the big game. So once you have that, you can show some interesting result. To do that, we defined, for example, we want to prove our result, MIP star equals to RE. What we are trying to do is to design, for any like Turing machine M, we want to design a protocol or to prove a game and to detect whether M is halting or not. And this is a decider that we define. And we use the so-called Connes Recursive Theorem. So Turing machine D halt is defined for a Turing machine M. And what it does is first you simulate this Turing machine M for n steps. The n is the index. If this Turing machine already terminates within n steps, then you accept. You know that it's terminating. Otherwise, you would compute a compression of itself. Like apply the compression procedure that compression theorem that we showed in the previous slide. So you can compress the game to obtain a compressed decider, and you accept only if the compressed decider accepts. So why this well-defined Turing machine is how where we used Connes Recursive Theorem. So we are in the specification of this Turing machine, we already need this the description of this Turing machine in defining this Turing machine. It's like a recursive call to itself, and that's something well defined and by Connes Recursive Theorem. So let's look at how we argue that if you do this, then we can claim that if that Turing machine M halts, then the value is 1. The the V hot is defined by this Turing machine on like a particular index where you can do this compression procedure. And if M does not hot, then the value is most half. The reason that this is 1 is we think of like Turing machine M hots in T steps, and T is some finite number. We can find an integer n so that T is in between n and 2n. Then by the compression theorem, well, first of all, we know that if like for this thing, the value of V hot on index 2 to the n has to be 1, because for 2 to the n, this game is simulating M for 2 to the n steps, and that's already bigger than T. So we know that M will hot and accept, and then the game accepts, because that's the decider, controls whether the game would accept or not. So that's value 1. But by the compression theorem, we know that these two values are the same. So the entangled value of this compressed game on smaller index is the same as the entangled value of the original verifier on 2 to the n index. So that's a compression theorem. So if this is 1, then compressed value is also 1. Now this equation is basically by definition. So if you look at what happens when you run this d hot on index n, because n is less than t, this first step won't accept, right? M simulate M for n steps, you haven't hit this threshold t yet, so nothing happens here. Now what you would do is you would compute the decider d sharp, and you would accept only if d sharp accepts. So that's how we have this equation. Basically, for this n, V hot is doing the same thing as V sharp n, right? So now if you look at these two steps, so the entangled value of this hotting game on index n would be the same as the hotting value of index 2 to the n, and you can basically go backwards. You can decrease this n until it hits n0. On the other hand, say if M does not hot at all, then we know that this step never accepts. By the entanglement condition that we have from the compression theorem, the compressed game on index n uses at least the amount of entanglement that original game of 2 to the n uses. That's important thing that we established for the entanglement bound in the compression theorem. Again, then by definition, this equation is by definition. Now, because this step is never accepting, so what d hot on n is doing is basically this compressed verifier is doing, right? So the amount of entanglement should be the same. And again, if you look at this step and that step, you can increase this index by raising this 2 to this power of previous index, so it can grow. You don't have any upper bound on this index. And also because we have like in the previous slide, we have this like some bound which only depends on n, and we can like change this n to 2 to the 2 to the 2 to the n, and that's how we argue that there's no finite amount of entanglement would give you a high value, and that's how we prove that the value should be low. And if you set the threshold correctly, it will be at most half. So that's how we like the compression theorem is really powerful. Once you have the compression theorem, this are like standard thing that you can do to argue that these games are really powerful. We can also give explicit separation between these two sets by giving you a game that a hyperplane that cuts in between these two sets. So this is how we define a new game called separation VSAP. And what it uses is it first computes the description of this n-not game. This is possible again using Klein's recursion theorem. You can take the description of DSAP here. Then we run the Mpa hierarchy. Remember, the Mpa hierarchy is giving you a sequence of values converging to the commuting operator value from above. So you do this Mpa hierarchy, and if Mpa halts, so if it detects that the value is lower than 1, then it halts, and then we accept. Otherwise, we would compress itself and do the trick that we did in the previous slide. And what we can claim is that the commuting value, the commuting operator value is 1, and the entangled value is the most half. This proof that the entangled value is the most half is the same as before, because let's first show that the commuting value is always 1. If it's less than 1, this means that the algorithm at step 2 would terminate for some amount of steps, because if the commuting value is lower than 1, then the Mpa hierarchy would detect this in certain number of steps, and then we would be able to accept. But if that's true, then we would be able to prove that the entangled value is actually 1. But the entangled value is always smaller than the commuting operator value, so it's a contradiction. This should never happen for this particular definition of the game. So you have commuting operator value being 1. And then, given that fact, you can argue that, oh, this step never happens, right? Because commuting operator value is 1, Mpa would never halt, no matter how big n is. And based on the same entanglement argument, you would be able to show that the entangled value is the most half. So this gives you explicit separation between these two sets. So proof techniques. The proofs techniques that we rely on are, first of all, the rigidity of nonlocal games, and sometimes also called self-testing. So basically what they are is we have, if the players have achieved the near optimal value, then they have to measure close to this honest measurement strategy. Now let's take this as an example. You have like a magic square game. This is a game you have 3 by 3 grid of variables, x1 to x9, and each row would have, so these are like binary plus minus 1 variables, and for each row you need the product of this variable to be 1, and for each column you need the product of the value to be minus 1. And obviously classically there's no such a solution, but when you convert it to a game, and the game is described in this box, you send Alice either a column or a row, and Bob a variable in it. And you accept if the row or column constraint is satisfied. So for each row, you should apply plus minus 1 values, the product to be 1, and for columns, the product should be minus 1. And you also check, for example, in our case here, the x6 is a common variable that both Alice and Bob are being asked. So we can check whether Alice and Bob give the same answer on this common variable. So that's a very simple game that you can play. And what we know is, even though there's no classical strategies for the game, there is an entangled strategy. The entangled value of this game equals 1. And that is one possible strategy where you use 2 EPRs, where EPRs are given here. It's like a 4-dimensional vector, and X and Z's are in quantum information theory, it's just these matrices. So I didn't write out all these operators because it would be tedious, but it's important that X1 and X5 in honest strategy, they are sigma X and sigma Z. These are the poly X and Z matrices. And so the rigidity for the magic square game is then that if you have a strategy that achieves value 1 minus epsilon, then you know that X1 and X5 that used in that strategy is approximately anti-commuting. And from that condition, there's that box, next box says that if you have two observables, reflections, they are approximately anti-commuting, then up to a local isomorphism, they are exactly the honest strategy X and Z, sigma X and sigma Z. So this is a very simple example of where you have approximate relations being satisfied, and which implies that up to some isomorphism, you can make this group relation exact. And that's, I guess, a connection that we had to operator algebra theory, that these are the non-trivial structures that we are using in our proofs. More generally, there's a paper by Gowers and Hatami. They prove a much more general result than this one. So basically, once this group structure is satisfied approximately, you can have an isomorphism so that you can, once you put this operators back, you would have exactly the representation of that finite group. But this more general result is not what we believe is not enough to prove the result, mainly because the efficiency that we need. What we do end up use is some efficient self-test for multiple qubits. So basically, it's a combination of the idea of rigidity and low degree tests that are introduced in the complexity theory slides. And so it's some known result from John Riddick and John Wright's paper. So the rigidity theorem, what this poly basis game, it's a new game, and what it achieves is some measurement. So it's a rigidity claim like this. So you can command the players to do poly X or Z measurement. W is X or Z. So that if they pass the test with 1 minus epsilon probability, then there is a local isomorphism, so that up to this isomorphism, this that the players use is actually the poly measurement. You can enforce this n qubits, NEPRs, this n qubit poly X and Z measurement, and it's efficient in the sense that the questions only have lengths poly log n if they are n qubits. For example, the results here usually it's not that efficient in terms of the question size. You would end up with some polynomial n question size because it's more a comparison would be like it's using linear functions, while here we are using polynomials in order to have such savings. And that's important for our compression, because what we are aiming for is to have smaller message sizes. Okay, so once we have this poly basis game, we are able to describe how we prove this compression theorem. It's a four-step procedure. So we start with initial game here. The first step is called introspection. What it does is to reduce the question size. So you end up with a game where the questions are much smaller, but the answers are still big and maybe even bigger. The second step is Oracleization. This is a pre-processing step. what it does is now there will be an Oracle player which plays the role of both Alice and Bob. So two players play at the same single player side. The next thing that are important is the Pcp Serum. So, like I've introduced the Pcp Serum to you before. Basically, what it can give you is to have a reduction in the messages, right? So this answer reduction step would reduce the answer size, and so we have much smaller gain, and also the verified running time is much smaller. Then the last step is called parallel repetition. So in this steps of transformations, we lose something called the gap. So 1 versus a half, and that's getting worse. So we have to recover that gap, and there is already like construction known in our literature known as parallel repetition. Basically, you would repeat this game in parallel many times, and you would check that all these individual gains are accepted by the verifier. So that's parallel repetition. So this introspection plus PCP idea is intuitively very interesting. And what it does is verify says that I'm lazy, and like how about you to provers come up with questions yourself, answer them. So initially the verifier should send the questions in the beginning, right? But now the verifier says you come up with the questions yourself and answer the questions and prove to me that I would have accepted the questions and answers. So that's a very interesting idea. First appeared in Turajan and Wright's paper. So I'll very briefly tell you how it works. So introspection is about the sampling of this question distribution. And this is how we model this distribution. This is a very non-trivial distribution, like Alice and Bob each have these questions. And this Z is some random seed. LA and LB are some functions. So we model this non-trivial distribution in this way. And in the end, we would want Z to be the sigma Z measurement on these EPRs. So desirable situation would be like this. The verifier simply sends intro A to Alice and intro B to Bob. These are very simple questions, like it's just a label. The player receiving intro V for V in A and B would apply a pair of strings Y and A. And Y would supposedly be this LV applied on Z. So if it's Alice, it's LA on Z. So meaning that the sampling is correct. And also we need that the answer A is answered in the original game for the question Y. Now, because the question is sampled by the prover itself, he or she should be able to give the answer once the question Y is sampled. And the difficult part is, of course, how do we ensure that the players would follow this kind of command, introspection command. So there are two ideas. One is how do we ensure that they measure X and Z? They do this honest Z measurement and apply a function. And most importantly, we also need to hide information when it's not necessary. Like in this two-prover model, Alice and Bob each has some information, and Alice's information is different from Bob's information. They are both computed from Z as a function of Z, but LA is not one-to-one function. So some information in Z should be hidden from Alice. And that's where we use Heisenberg uncertainty principle. So here is a very simple example. Say, like this Z measurement on the EPR would give you a random 0 and 1. You know this information. And how do you hide this information from Bob is you ask Bob to measure X on that qubit. If Alice measures Z and the state collapses to 0, and Bob would have 0, but once Bob measures X, it will be a random plus and minus, and this 0 and 1 information would be erased from Bob's side. So a combination of these two and a lot of proof would give you this powerful primitive that you can command the provers to do this introspection. Then in the answer reduction step, so basically it's what we have seen like in the Pcp theorem. You don't send back this big proof. You would only send back a Pcp of that fact that decider accepts. So that's what we use in our proof. So the last ingredient, or actually this is what is new in this paper of MIP star equals to IE, is we have to make this compression recursive. The reason for this is that like in defining this halting to a machine, for example, I have use this compression in this form, like compress S sharp D hot to give you S sharp and D sharp. And this is not something that any compressed procedure can guarantee you, because somehow we are using the fact that you can choose a universal sampler here. This S sharp is universal, and that's another technical issue that we need to solve, that it's essentially we are able to find some sort of fixed point of this procedure. There's some universal distribution that works for this family of games that we are interested in. The idea is also very simple. You have a procedure, you're starting with introspection. And of course, there is certain structure of distribution that you can introspectively sample. That's one thing. So that's what introspection step can handle as an input distribution. Another distribution is after this compression procedure, like there's 4 steps, there will be a much more complicated distribution, and that's the output of this, the distribution of the output gain. We want to make sure that these two are the same, a uniform normal form framework for the input distribution and the output distribution. And technically, that's what we found out to be the solution. It's called conditional linear distributions. You can make it so that these two are the same, both modeled in this framework. I don't have time to give you details of this definition, but it's a very simple definition: extension of linear functions. So to conclude, I've claimed that there's a recursive gap-preserving compression procedure of 2 proof of 1 round particles, and from this, and using Kleen's recursion theorem, you are able to show that like RE is in MIP star. You can reduce the problem of whether a Turing machine terminates or not to a MIP star particle. And then the equality follows from the containment in RE by the algorithm 1 that we talked about earlier. And by the known connections, the complexity of computability consequences of Tsirelson's problem, we gave negative answers to these 2 problems. There are several open problems. One is simpler proofs. Proof is really long and use a lot of intuitions in quantum information theory. Maybe it's not friendly to mathematicians. So I think it's valuable to find a simpler proof for this result. Also, there's a class related to MIP star called MIP co. Basically, you would consider the correlations to be commuting operator correlations. And we conjecture that this class has a nice characterization, the co-RE. Note that these 2 codes are different, have different meanings. Also, interest in open problem is to give explicit counterexamples to Connes embedding problem, which are, even though we know that we give negative answers, it's through a long chain of complexity theory to Tsirelson's problem and then to Connes. So it's not an explicit counterexample. And to summarize, I think it's an interesting slide to show you. Like in physics, in the 30s, the EPR paradox and entanglement are being proposed by Einstein, Podolsky, Tsirelson, and in the 60s, Bell inequalities is proposed by Bell, and in the 90s, Tsirelson proposed this Tsirelson's problem. In computer science, again, in the 30s, Turing invented the Turing machine and studied Halting problem, and complexity theory developed in the 70s, and a lot of interesting stuff happening in the 90s, arriving at the Pcp Serum. In mathematics, again, in the 30s, I guess not a coincidence, von Neumann is trying to lay the foundation of quantum mechanics, and Alan Kohn proposed this problem in the 70s, and there are a lot of later development. I guess you would know more about this topic than I am, and all these are related to this single result, where we use a lot of ideas and techniques in computer science and quantum information, and have consequences in mathematics, which is really a surprise to me and to, I guess, to all of the courses that in the beginning we wouldn't have believed that this approach would worked in this way. So thank you for your time. I guess it's about the time. I'll stop here, and if you have any questions, I'm happy to answer them.